Okay guys, let's go ahead and go over the warm-up questions for today. Should be pretty straightforward because they came straight from yesterday's notes. We'll go over these, and then we have notes today on impulse momentum theorem, and you do have an assignment for the end of the class period today, 502.2 momentum and impulse problem set. I am going to encourage you to jot down some notes today, because as we go through the notes that we're going to cover in class today, there are a lot of misconceptions that students have that are kind of contained in this material. So I'm going to very strongly encourage you to write it down and to make sure that you're listening and paying attention so that you don't miss the questions in this assignment. And so that you are better prepared for your test, which, by the way, if you haven't been looking, your test is a week from tomorrow. So we have notes today, we have notes tomorrow. We'll take notes on Monday. Tuesday and Wednesday of next week, you will be working on a relevant application, so like a lab project. And so we won't be doing new material then, but on Thursday, you'll have your CFU, the times whenever we take like the quiz in my open math, it's going to be like one of those where you can work with other people if you want, but you only get one shot at each question, and then your test will be the following day. So that's kind of where we're going. There's not a whole lot of material in this unit, so it's obviously important that you are paying attention to the stuff today so that you feel good about it. Hopefully yesterday you feel good about, and as we move forward, because it's really just impulse and momentum, and we already know those. We're just going to start applying it to some other types of scenarios and bringing in some other stuff with it. So let's go ahead and go over the warm-up first, and then we'll go ahead and get into the notes. So hopefully you have a notebook out. If not, please do that while we talk about this. So today's warm-up question says, if a 5-kilogram ball is moving 5 meters per second, what is its momentum? And you're just going to use the equation that we learned yesterday. Momentum is mass times velocity, P equals M times V. And I gave you a mass and a velocity in the question. So it's 5 times 5. 5 kilograms times 5 meters per second gives me 25 kilograms times meters per second. So that is your answer to number 1. Just multiply the numbers and multiply the units. So 25 kilogram meters per second. Number 2 says, what could cause its momentum to change? We talked about this yesterday as well. You can have a change in momentum if you have acceleration, which is going to be due to a net force. If you apply an impulse, a force, for a certain amount of time and cause acceleration. Something along those lines should be your answer for number 2, because if you want to change momentum, you need to change velocity. Okay, and so how do you do that? Again, you need acceleration, which means you need a force. Are there any questions about the warm-up? All right, then as I said, we have some notes today. We're going to start with the impulse momentum theorem, which tells us that the impulse applied to an object will be equal to that object's change in momentum. Okay, and I said this yesterday in the notes, so that should not be a new statement to you, but we did not write it mathematically. Okay, so because they're equal, we can take those two equations that we learned yesterday. We know impulse is force times time, and we know that change in momentum is mass times change in velocity, and we can set those equal to each other. Okay, and that's what I've done up here on the screen. Force times time, that's my impulse, equals mass times change in velocity, that is my change in momentum. That's all it is. Okay, so it's just one new thing, and it's not even really that new. It's the equations from yesterday, and we're just going to set them equal to each other. Okay, so impulse is equal to momentum, or change in momentum of an object. Change in momentum is equal to the impulse of the object. This equation shows us that a small net force applied over a long period of time can be used to produce the same velocity change as a large net force applied over a short period of time. And that is going to be most of our conversation today, is going to be about how in a given interaction or collision between objects, we can have this trade-off between force and time, but our impulse is going to be the same for a given set of conditions for the collision. So we'll see more of that later, but believe me, you're going to see force and time in this a lot today. All right, starting right here. Okay, so this particular question says, or scenario says, a 10,000 kilogram truck moving 30 meters per second comes to a stop in each of the scenarios below. one of them by hitting a pile of hay and the other by hitting a wall. And so we have an image there showing those trucks that are driving. One of them comes to a stop after it runs into a pile of hay. The other one comes to a stop whenever it hits this wall. You've got two questions here to think about, and it says which truck has greater mass and which has a greater change in velocity. The first question is probably pretty straightforward, but you might want to turn and talk to your neighbor about the second one at least. Which has a greater mass, which has a greater change in velocity? Please turn and talk. You have 25 seconds. All right, so which has a greater mass? Well, the question says that you have the same truck. So they have the same mass. That's the answer to the first question. And again, that's one that you probably didn't really need to discuss. But what did you guys say for the second one? Which one has a greater change in velocity? I hear whispers. Which one has a greater change in velocity? What'd you say? The same. Okay, I heard some of you saying the one that hits the wall. Okay, the one that hits the wall absolutely has a change in velocity faster. The rate of change in velocity is a greater rate of change. However, the question says that these trucks are both moving 30 meters per second initially, and at the end they have both come to a stop. And so both of them have a change in velocity of negative 30 meters per second. They have the same mass. They have the same change in velocity. They have very different results. Okay, and again, that has to do with the fact that you have more time to come to a stop if you hit a pile of hay than you do if you hit a wall. But let's get to the other part of this discussion first. If you have the same mass and the same change in velocity, then you have the same impulse. Because impulse is change in momentum, and change in momentum is mass times change in velocity. So if we have the same mass and we have the same change in velocity, we have the same change in momentum, and therefore we have the same impulse. Impulse is force times time. In these two scenarios, the time is very different. This one at the top, if you hit something that has give to it, that will move with you like a pile of hay, you're going to take longer to come to a stop. So there's more time. When you hit a wall or a very hard object, whatever it is, you're going to stop instantly. There's very small time. And so the impulse is the same, but because the time is different, so are your forces. Up here, this large time means that there's a small amount of force, at least relatively so, applied to this truck versus this truck that stops in a very quick amount of time, very short time, has a very large force because of that. So again, the force times time equals the force times time. They have the same impulse, but because those times are different, their forces are different as well. Okay, and I told you we were going to talk about this several times throughout the notes today. So you have a chance to write it down again if you didn't get it there. Here's a similar type of scenario. This one says a moving truck is traveling down the road and approaches a stop sign. The driver applies a force to the brake and the truck slows to a stop in 5 seconds. If this truck later needs to stop in half the time to avoid hitting the dog, how would the force required compare? So there's a dog in the roadway here. He only has half as much time to stop. Does he need more force or less force? More. If he needs to stop in half the time, he's going to need more force. But again, we can look at why that is. It's the same truck, so the masses are the same. The change in velocity, we're going to assume that these trucks are traveling the same velocities initially, and both of them come into a stop, because that's the only way we can compare the scenarios. I should have listed that in the question, and I didn't. But we're going to say that they have the same mass and same change in velocity, and thus they have the same change in momentum and the same impulse. So the impulse of the truck that's stopping at the stop sign equals the impulse of the truck that's stopping to avoid the dog. Okay, so there's the same impulse, just like in the last scenario. Okay, and impulse, again, is force times time. So in this scenario, he has more time to come to a stop, and so less force is required. Whereas in this scenario, he has less time to come to a stop, and therefore more force is required. How much more? If you need to stop in half the time, you will need 2 times the force, because force and time are inversely proportional to one another for a given impulse. Okay, you do need to know how to answer these types of questions that ask you to use proportional reasoning. So 2 times the force for half the time. Again, it's an inversely proportional relationship. I even made that very obvious. When this one's small, this one's big. They're opposite. Same thing over here. Questions about this? All right. You've seen this one before. Okay, we're again bringing stuff back in. While driving, Miss Darwin observed a bug striking the windshield of her car. The bug hits the windshield hits the bug. Which of those forces is greater, the force on the bug or the force on the windshield? You've seen this exact question before. Which one is greater? What'd you say, Gabby? Neither. They're the same. Again, this goes back to Newton's third law. This is a force pair, guys. For every action, there's an equal and opposite reaction. That bug and that car have equal and opposite forces. You need to remember that from our forces unit. They're equal. Okay, what about their impulses, though? What about some of these other things we just talked about? Okay, so now I have a couple of statements on my screen. There's a couple more on the next slide, and it's the same scenario, and it says to tell whether the following statements are true or false and why. A says the force of impact of the bug on the car and the car on the bug are the same size. We just said that was true. That's a force pair. Those forces are equal and opposite. They're the same size. But the second statement is talking about impulse. The impulse on the bug and on the car are the same size. Do they have the same impulse? Okay, well, they have the same force. An impulse is force times time. So do they have the same time? Is it possible for the bug to be touching the car for a different amount of time than the car touches the bug? No, because they're touching each other. Okay, and so the time will be the same because it's the same collision. The forces are the same because it's the same collision. If your force is the same and your time is the same, your impulse is the same. This is a true statement. Just like you have equal and opposite forces in a collision, you have equal and opposite impulses in a collision. Okay, so again, this is a true statement. Let's look at the next one. The change in speed of the bug and the car are the same size. Is that true? Is the change in speed the same? Dylan, what do you think?
Yeah.
Do they have the same mass? No. Okay, so they have the same impulse, they have the same change in momentum, but they don't have the same mass. Remember, change in momentum is mass times change in velocity. If they don't have the same mass, they can't have the same change in velocity. Okay, we've talked about this similarly whenever we did it in the forces unit, because we talked about acceleration specifically, and the bug has much more acceleration than the car. Same idea. The bug has a much greater change in velocity than the car. Okay, and so this one was a false statement. The last one says the change in momentum of the bug and car are the same size. Change in momentum is equal to impulse, so this has to be a true statement. We've already answered this question in part B. In part B, you told me they had the same impulse, so in part D, you better tell me that they also have the same change in momentum. You're going to see that question multiple times where I ask you, hey, here's a scenario, which one has a greater impulse? And then later on I'm going to say which one has a greater change in momentum, and you need to know, hey, that's going to be the same answer. Okay, it's going to be the same thing because your impulse is equal to your change in momentum. That's the first slide today of today's notes. They're equal to each other. Questions about this scenario? All right, this is going to summarize it all if you want to write it down here, but looking at this collision, we can look at and analyze the force, the impulse, the change in momentum, acceleration. I'm sure there are other things too, but looking at this, I know that the force on the car equals the force on the bug. We have a force pair. I know that the impulse is equal for each as well because we have a force pair, because the forces are equal and the times are equal, the impulses are equal, thus F times T for the bug equals F times T for the car. The change in momentum is the same thing as impulse, so if my impulses are equal, so is my change in momentum. Change in momentum is mass times change in velocity. This car has a large mass, thus it must have a small change in velocity, whereas this bug has a small mass and thus it must have a large change in velocity because these two have to be equal to each other. M times delta V for the bug has to equal M times delta V for the car. Okay, so, and I have it up here as car equals bug, but same thing, these need to be equal. But my change in velocity isn't equal, and neither is my acceleration. This last one, acceleration, because I know my forces are equal, and because force equals mass times acceleration, I can say mass times acceleration equals mass times acceleration. But again, they have very different masses. This very large car with this large mass will have a small acceleration. On the other hand, this very small bug with this small mass will have a very large acceleration. And we talked about this in the last unit. It's the same thing. Okay, we're not making anything new. It's the same thing we've already discussed. Okay, and so MA equals MA. Again, you might want to write this down. In a collision between two objects, each will experience the same magnitude of impulse. I've said it already. It's up there on the screen, but you might want to actually write that down as a sentence in your notes as well. You will have equal and opposite forces. You will also have equal and opposite impulses. Okay, because the forces are equal and opposite, so will the impulse. It will also be equal and opposite. All right, so you've seen this collision before. I want to look at one that looks a little different than the ones we have seen before because you're going to see other types as well. And so let's look at another scenario where I have two people standing on ice skates that push off of each other. That's still a collision. We don't think of it as much of a collision as, crashing into something, but pushing off of somebody is going to be, in terms of physics, a collision. Okay, and so it says two skaters are at rest on ice when they push off one another and move apart as shown above. If you were to try this, that's exactly what would happen. If you push off of another person, you will both slide away from each other if you're on ice. Okay, and so we're going to do the same thing. We're going to talk about the forces on the man versus the woman, the impulses on the man versus the woman, the change in momentum, and the acceleration. Okay, so let's talk about force first. Who has more force, the man or the woman? What do you think, Brian? More force. Same. Good. Third law. Force on the man equals force on the woman. Okay. Impulse. We just said this. Impulses will be the same as well. The force times time, the impulse on the man will be equal to the force times time, the impulse on the woman, because the forces are equal. Okay. Change in momentum is equal to impulse. So if my impulses are equal, so are my changes in momenta. Okay, and so change in momentum is mass times change in velocity, but their masses aren't the same. At least they don't appear to be. It doesn't say, but he looks like he has more mass than her. He's taller. He looks like he's a little bit bigger than she is. Okay, so we're going to say that he has more mass, and thus a smaller change in velocity. She has less mass, and thus a larger change in velocity. But the product of the two, mass times change in velocity for the man, needs to equal mass times change in velocity for the woman. They have the same change in momentum. Okay, acceleration, not going to be the same. Because they don't have the same change in velocity, of course they're not going to have the same acceleration either. Okay, but again, you can see that this way. MA equals MA, but this time, because my masses aren't equal, his large mass will have smaller acceleration, her smaller mass will have a larger acceleration. It looks exactly the same as the last collision. Same equality statements are up there. Okay, so they won't have the same acceleration, but they will have the same force, impulse, momentum change. It's just the acceleration and the change in velocities that are going to be different. Okay, so we can do this, with any scenario. It's always going to look like that if you're talking about a collision between two objects. Okay, but I'm going to put some numbers to it, and we'll see if we can do a calculation with this. Okay, so same scenario, this man and this woman still on ice, still moving apart, and now it says if the man has a mass of 85 kilograms and the push causes him to accelerate to a speed of 5 meters per second, with what speed will the 70 kilogram woman move following the push? Okay, she has less mass than him. He's 85, she's 70. We already determined that when their masses are different, they're going to have different changes in velocity. She's going to move faster than he is because she has less mass. We just looked at that on the last slide. But if I actually want to determine how fast, I need to calculate it, and I'm going to use the equation from the last slide. His mass times his change in velocity will equal her mass times her change in velocity, because we have already determined that in a given collision we have equal impulses and thus equal changes in momentum. So this is his change in momentum. He has a bigger mass, smaller change in velocity. This is hers, smaller mass, larger change in velocity. But let's put some numbers in. 85 is his mass. His speed afterward is 5. Okay, that's his change in velocity as well, because he started at rest. So he started at rest, now he's going 5, his change is 5. Okay, her mass is 70, we're looking for her change in velocity. So 85 times 5 is 425, it is equal to 70 times delta V. If I want to solve for the change in velocity, I need to divide both sides by 70. 425 divided by 70 gives me a change in velocity of 6.07 meters per second. But my question wasn't what's the change in velocity, my question is how fast is she going after the push? Well, how fast was she going initially? Catalina, how fast was she going initially? What's it say? Right here. At rest. Right? 0. Okay, so they're initially moving 0. So if her change is 6.07, well, guess what? Her speed is 6.07 meters per second. Okay, I don't care about which direction for speed. It's a scalar quantity, so I'm just looking at the magnitudes in this calculation. Okay, so the magnitude of her velocity is 6.07 meters per second. The magnitude of his velocity is 5 meters per second. Of course, they're going in opposite directions. Does anybody have a question about the calculation? You will see a question like this later on in your assignment. I don't know if it's today's assignment. It might be one tomorrow or on Monday, and potentially on your CFU and on your test. So just be aware, write it down, have it to look at in case you get stuck. All right, so we're looking at these collisions where you have these two objects colliding with each other. They have the same force at the same time. Now we're going to look at different types of collisions kind of side by side. And this animation is from the video that I suggested that you watch the other day, yesterday. There was that physics of car crashes video. And I took and snipped this animation from the video. So in this demonstration, he is throwing an egg at two different surfaces. He's throwing an egg at a wall, and of course it's going to break and splatter. And then he throws that same egg or similar egg at a bed sheet. Okay, and so you see very different results here, because the one that hits the wall splatters, the one that hits the bed sheet doesn't even break. Okay, and so the reason for this is that these have different stopping times. Okay, they're not colliding with each other. It's not like the last one. This is like the first example with the truck that hits the hay versus the truck that hits the wall. Except now it's an egg that hits a sheet versus an egg that hits a wall. Okay, but the time that it takes to stop is different, and therefore the results are different. This one that hits the wall stops in an instant. Okay, the one that hits the bed sheet, because the bed sheet has give to it and it moves with it, it's able to keep moving forward a little bit longer. It doesn't stop as fast, and therefore it doesn't have the same time of that or the same acceleration or the same force. Okay, so again, it says this up here, the manner in which you bring something to rest matters. If you give it more time to come to rest, you're going to apply less force to it. Let's look at it in terms that you've already seen. Okay, again, this is the same impulse. If it's the same egg, has the same mass. Okay, and let's assume he throws it at the same initial speed, then the change in velocity will be the same. They both come to a stop. Okay, it's just that for this one that hits the wall, the time that happens over is very short, and so the force has to be very large. Whereas the sheet, the time that happens is longer, and therefore the force is much smaller. Okay, so again, we're looking at this exchange between force and time. Trying to lengthen the amount of time of the collision is going to lessen the force that the egg feels, or the truck that hit the hay felt, or whatever it may be. We're going to look at different scenarios. Again, both of these have the same impulse. They had the same mass. We're going to assume they had the same initial velocity and therefore the same change in velocity. So this Ft equals this Ft. The difference is the times are different, and therefore the forces are different. Here's another type of question you might be asked about with collisions. So we've looked at the time of the collision and how those conditions can change it. We've looked at collisions where you have two things colliding with each other, and now we're going to look at what if it bounces instead of staying there after the collision. Okay, I don't know how many of you guys have done like paintball. Who's done paintball in here? Have you ever had a paintball hit you and bounce off? Doesn't that hurt like way more than if it just bursts? If you haven't done paintball, what about a water balloon? Have you ever had a water balloon hit you and bounce off instead of popping? It hurts more. It like slaps your leg and then bounces off, and it hurts more. Okay, and so this question is, why do you think that happens? Why do you think that a paintball or water balloon that bounces off of you hurts more instead of one that bursts? Anybody have a guess? We haven't talked about it yet, but I'm just curious. Not sure? That's okay. Let's look at why that is. Okay, so why does that happen? Okay, here's a different scenario with something that bounces, but I have it up here at the top. Bouncing means more force. Okay, let's look at why that is. This is showing a billiard ball that hits the rail on a pool table and then bounces back. Okay, it says the ball experiences more acceleration and thus more force if it bounces. And this is easier to see with numbers. So let's look at some numbers. If the ball was to stop, this one doesn't, but let's pretend for a second that it stops. Let's say it's going 5 meters per second initially and it stops. Okay, versus one that bounces. This one still going 5 meters per second initially, but now I'm going to say, hey, it bounces back with a final velocity of 3. But that's the other direction. If it bounces backwards, your sign needs to be different. Okay, so my initial's 5, my final's -3. All right, so I have these two different scenarios. My change in velocity for the ball that stops is -5. My change in velocity for the ball that bounces, on the other hand, it's not 2, it's -8. To go from 5 to -3 is a change of -8. Okay, that is a greater change in velocity if we assume, and I have to tell you this, but if we assume that this happens in the same amount of time. Okay, the bounce versus the stopping. Okay, if it happens in an equal amount of time, then this larger change in velocity means that we have more acceleration, and more acceleration means more force. F net equals ma. More acceleration, more force. More force means more impulse. Impulse is F times t. That's why it hurts more if it bounces. If you have a ball or a paintball, a pool ball, a water balloon, whatever, if something hits you and bounces off, that is more force applied to you than if it was to just stop and stick to you or burst on you or whatever it may be. Okay, so again, bouncing is a bad thing. You don't want things, in terms of your safety, you don't want things to bounce off of you. You don't want in a car crash, you don't want your car to bounce off of whatever you hit. You don't want your head to bounce off of the glass. None of that. All those things are bad because they mean more acceleration, more force, more injury because of that. All right, let's look at car crash. I told you guys one of the best real-world examples that we talk about in physics is actually in this unit. Okay, I mean, all this stuff is real world, but car crashes is something that is definitely important and pertinent in real world experience because everybody in here gets in a car at some point every day probably. Okay, it says, so if you're in a 1,500 kilogram car traveling 30 meters per second, which is about 67 miles per hour, so we're talking freeway speeds, and you get in a crash that brings you to a stop, we can find your impulse. Again, impulse is equal to force times time, but it's also equal to mass times change in velocity. So that's what I did because that's what I have. I have the mass, 1,500, and if I go from 30 meters per second to 0, my change in velocity is -30. 1,500 times -30 is -45,000 Newton seconds. Okay, so that would be my impulse if I get in a car crash. What if I brake normally? To bring the same car, driving the same speed, but instead of hitting something, I just put on my brakes and I slow down and I come to rest over 10 seconds. What is my impulse then? Is it more or less, is it the same? Well, look at the equation, guys. Mass times change in velocity. I didn't change the mass, and it's not a different velocity either. You have exactly the same impulse. whether you get in a wreck, or crash into something, or brake normally. In fact, it doesn't matter how you stop. Okay, if you were traveling in that car with that mass at that speed, no matter how you stop, this will be your impulse. Okay, whether you hit a wall, whether you brake normally, whether you hit another vehicle, whether you're wearing your seatbelt, whether you have airbags, it doesn't matter. That's the impulse for that set of conditions, for that collision, or for that stopping, okay, whatever, for that scenario. Okay, so again, your impulse is going to be determined based on how fast you're going and your mass. And guys, you're going to want to write this down. This is the real world stuff that you need to know. You actually have an RA next week, and you're going to need to know this for that too. The impulse you experience is determined by how fast you're driving and your mass. We just looked at it. Okay, it didn't matter if you crashed or if you stopped normally. Your mass and your change in velocity determined your impulse. Okay, and so that's what is going to determine the impulse you experience. Now, that's not something that your car, that an engineer can address. Okay, but whenever they design car safety features, not to reduce the impulse, because the impulse, again, that's depending on how fast you're driving. Okay, ultimately, and they're assuming you're going to drive at the posted speed limit. Now, whether or not that's true, different story. Okay, but if you're driving at that posted speed, okay, there's a certain impulse you should expect if you stop, whether you hit something or not. Okay, they can't control that. What they do instead is these car safety, the engineers that work on the cars, they design features in the car, like crumple zones or airbags, that are designed to decrease the forces that you feel because they increase the time that it takes you to slow down. Because the impulse is basically set for that collision. It's based on your speed and your mass. Okay, that's not going to change. You're theoretically driving the speed limit. Again, theoretically. Hopefully you're close to the speed limit. So what they do instead is they put like a crumple zone at the front of your car. Guys, when you get in a wreck, the front of your car is supposed to crumple. You don't want it to stay rigid. That's a bad thing for you, because if it stays rigid, that's like the truck that hits the wall or the egg that hits the wall. If it has give to it, if it crumples, then you still get to move forward a little bit longer, and it lengthens the amount of time it takes to bring you to a stop, like hitting the hay or hitting the sheet with the egg. Okay, you want that. You want more time to stop. So your car is designed to crumple. The airbag does the same thing with your body. Okay, your body's moving forward. The airbag is designed to slow you down more gradually as compared to hitting a windshield or a steering wheel or something like that. Okay, because the airbag has give to it. Okay, and so it will move with you, but it means that you have more time to stop, and thereby it decreases the forces on you because of that. Okay, so this is that same relationship between force and time. We're coming back to it again and again because it's super important. It's not just your car safety features though. Okay, football players wear helmets and pads for the same reason. They have some give to them. There's foam padding inside of it in the helmet so that you still move before your head stops as if it hit the pavement or something. Of course, you're not on pavement, but it has give to it. Okay, or gymnastics mats. Okay, if you do a flip off of a balance beam onto the ground versus onto a mat, that mat has give to it. Or even just the way you land. You don't lock your knees when you jump and land. You bend them so that you get to move a little bit more, and there's a little bit of give to it before you stop. Okay, all of it is about force and time. So this video clip is from Mississippi State football. They're going to talk about the same concept with the padding in a football helmet, okay, with impulse. Okay.
Last time we looked at how pads use pressure to distribute the force of the blow over a larger area. Well, there's another physics concept at work here called impulse. We can see how it works with a football helmet. You guys want to help me out? Listen. Impulse is the force felt during a collision, multiplied by the duration of the collision. In a given collision, the impulse will be the same, but this can happen the hard way or the easy way. You can't hold that, Mr. Warner. Don't worry, I've done this a million times. If you'll hand me that melon. If the duration of the impact is short, then the force felt will be large. Oh, exactly. The impact with the ground happened almost instantaneously, and the force was very large enough to burst the melon. If you'll hand me that melon and helmet. The foam padding inside the helmet increases the duration of the collision, decreasing the force felt. So the melon's perfectly unharmed. So, according to the physics principles of pressure and impulse, I should be perfectly safe.
You probably should have fastened the helmet, but again, it's the same idea. Those pads in there, rather than your head hitting something hard and stopping immediately, your head can keep moving a little bit as it compresses that padding inside, and that gives you just a little bit more impact time, and a little bit more impact time could mean, a lot less force. Even if it's just, twice as much time to stop, you only have half the force then. Okay, so again, same principle, but looking at it in another scenario, another application. All right, I don't even know how to make that stop. Okay, I'll figure that out later. So this has, it says a crash test lab gathers data for 3 collisions involving a crash test dummy. They gather data and graph the forces when the dummy collides with the windshield, the airbag, and a padded dashboard. So these are graphs that you could potentially get, and guys, you're going to get graphs just like this when you do the RA next week. This is what force time graphs look like. Okay, so looking at this, if those were the 3 scenarios, if one of these is a windshield, one is an airbag, and one is a dashboard, which one of these graphs do you think would show the collision with the airbag? A, B, or C? What do you guys think back there, Luke? C. Yeah, C would be the one, if those were the 3 scenarios, C would be the one with the airbag, because the airbag has the most give to it. It's going to allow you the most time to stop, and when you do that, it reduces the force. Obviously, you'd rather hit the airbag than the windshield. Okay, the padded dashboard's slightly better than the windshield, but it would still have a fair amount of force. Those padded dashboards don't have a whole lot of give, but a little bit. Okay, but you would expect the airbag to do something like this, and that's what your goal's gonna be in the RA, which we'll talk about later. Okay, so let's go ahead and talk about these graphs a little bit more. Okay, these are force time graphs. Okay, we haven't looked at force time graphs before, but this is pretty much what they look like. Okay, I mean, they're not quite that smooth whenever we gather it with our force sensors, but they'll be pretty close to that shape. Impulse is force times time, and thus impulse is the area under the curve on these FT graphs. Anytime you are trying to solve for something and it's the x and y axes, so y times x, that means find area. If you're multiplying your axes, find the area. So you need to make a note. Impulse is the area of a force time graph. Now, I know that you guys don't have the ability to calculate the area under those curves because you need calculus. Okay, so what we're going to do instead is we're going to approximate them with triangles. It's about like that. They're about triangles, so they're pretty close. So we're going to use these 3 triangles instead. Okay, and we're going to find the area of these because I know y'all know how to find area of a triangle. 1/2 base times height. So looking at the first one, again, I'm looking for area because J equals F times T, we're finding area. 1/2, my base here is 2, my height here is 12. 1/2, 2 times 12 is 12. Okay, what about the second one? 1/2 base times height, this time my base is 4, from 2 to 6 is 4. The height is 6, 1/2, 4 times 6, guess what? Still 12. Because we're talking about the same collision. Okay, remember, it's going to be the same impulse. So guess what this one's going to be? 12. 1/2, 8 times 3, still 12. Okay, whether you stop, or this crash test dummy stops with the windshield, the airbag, or the dashboard, it's still the same impulse in each of them. Okay, it's just you'd rather be in this situation instead, because that's a lot less force applied to you. Now, these aren't real numbers for a car crash. They're very small for a crash, but it's the right idea. Okay, so if you have a force time graph, find the area, that's your impulse. I could also ask you to do a calculation with that. And again, I already said this, but these all show equal impulses spread over different times. Let's look at a calculation with the graph like this. I'm going to assume now I'm not looking at a car crash because the numbers aren't right for that. I'm going to say this is a bowling ball. And it says if this graph shows the impulse on a 7.2 kilogram bowling ball, find its change in velocity. Okay, so you should be able to do calculations where you have to get information from a graph to do them. This is a good example of that. We'll have another one in a second where we have to get information from a data table. Same idea, but we're going to start with our equation. Again, impulse is mass times change in velocity, or force times time, but in this case, I have I'm looking for change in velocity. And I already know the impulse. I already used force times time. The impulse is 12. We already found it. It's the area. So I'm going to plug in 12 equals, here's my mass, 7.2 times delta V. We're looking for change in velocity. We're going to divide both sides by 7.2. 12 divided by 7.2 is 1.67 meters per second. So the change in velocity of this bowling ball would be 1.67 meters per second based on that graph. Okay, does anybody have a question about this one? Again, you should be able to use a graph to pull information from in order to do any calculation that I can give you. All right, let's look at one more and then you'll be working on your stuff. This one though, I have a data table instead. Same thing though, you should be able to get information from this data table to answer the question. This one says the motion of a 5 kilogram object is given below. What force does it experience from 2 to 4 seconds? So I don't care about the whole table, I only care about 2 to 4 seconds. So let's go ahead and label what we know. We know the mass is 5. We know from 2 to 4 seconds, that's a 2-second window. So the duration of this particular, in this question, is going to be 2 seconds. Okay, from 2 to 4, that's a 2-second window. I know that at that 2-second mark, my initial velocity at that point is 12. Okay, because I'm only looking from 2 to 4, I'm going to start at 2, 12. At 4, my final velocity is 4. I could have asked you for any interval, by the way. I could have said from 0 to 5, and then you would have used those numbers. Okay, but this is what I'm using. All right, so I have mass, I have time, I have initial final velocity. I am looking for force. My equation for this, based on the information I have, I'm going to use this equation we started the class period off with. F times t, impulse, equals m times delta v, change in momentum. So this is my impulse momentum theorem. Okay, but I don't have delta v, I have vi and vf, but delta v is just vf minus vi. So you can either subtract it first and then plug it in, or you can actually plug it in as vf minus vi, which is what I'm going to do. F times 2, that's my force times my time, equals my mass times change in velocity, 4 minus 12. Okay, which I know is negative 8. Again, I went from 12 to 4, that's a change of negative 8. 2F equals negative 40, divide both sides by 2, and I get a force of negative 20 newtons. Does anyone have a question about this calculation? Again, you will see this again. It's in your assignment today. Different numbers, but it's in your assignment today. Okay, so if you have a question, you can look back at it, or of course you can ask. Speaking of your assignment today, for the remaining time you have left in the class period, you should be working on 502.2, Momentum and Impulse Problem Set. If you do not finish this during the class period today, you need to complete it for homework. It is due by 11:59 p.m. tonight.